have Steffen Gielen today to talk to us about the cosmological framework for quantum gravity. Steffen just joined the School of Maths as a Royal Society fellow, so you'll be seeing a lot more of him. I'll let him start.
All right. Okay, so thanks Thomas for the introduction. Thanks for organizing this, and thanks all of you for being here. I don't know very much about the format of this seminar, but the way I see it is just that I'm trying to give you some glimpse of what my research is about in the context of a relatively simple model, and I will try to avoid too many technical details. So it should be nice and easy. I don't have too much time. Timing will be strict. So I will try to keep it short. And of course, if you want to know more about anything I'm saying, you should just ask me. And I hope it's interesting for everyone with the mixed backgrounds of people that I recognize. So the project that I'm discussing here was basically a master's project. So at the Perimeter Institute they have this one-year master's which they call Psi, and the students are doing what's called an essay. So this is a bit like the dissertation here. So they have about 3 months or so. So we had a very good student last year. So the name of the student is Eugene Ajay. And Wolfgang Wieland is a postdoc at the Perimeter. So he was also involved in this, and so this was a master's project which then turned into this paper which is now on the archive. Just to give you some motivation, so the idea is of course in the title, I'm just trying to explore somehow a possible connection of quantum geometry, a theory in which space is somehow quantized and emergent from discrete structures fundamentally, which is of course a very general idea in quantum gravity. And here I'm trying to connect this idea to cosmology in the context of just a homogeneous isotropic universe. So the very simplest cosmology that you can possibly think of. So the type of model that I'm thinking of is basically a type of matrix model. You could see it as a type of matrix model. So the general idea, as I said, is somehow fundamentally there are discrete structures and combinatorial structures, and what we see as geometry and space-time somehow emerges from a very large number of these very complicated structures of this type in some continuum limit. And the prime example that people always give for this idea where it has actually worked is in the context of matrix models, right, in two-dimensional quantum gravity. So let me just remind you how that works, just in a very simplistic way. So what you have is a theory of matrices. So I'm just calling this M. So this can be some n by n Hermitian matrix, for example. And you cook up some action here for a matrix and say the Hermitian conjugate, which defines some kind of elementary dynamics, right? There's really no structure here, there's no space-time or anything. They're just these matrices that have some kind of dynamics, right? And so then if you do this quantum mechanically, you write down something like a partition function here, where you integrate over the space of these matrices, and you do this Euclidean, for example, you weight them with this action here that you have introduced. And the way to see that this has something to do with two-dimensional quantum gravity is, well, there are many ways of doing that, but a simple way is to expand this partition function in Feynman graphs. So you do your usual perturbative expansion, right, in M if you want, and you get a sum over Feynman graphs. And now the point is that basically each of these, so these Feynman graphs are basically vacuum bubbles, right? Because this is just a vacuum partition function. And each of these Feynman graphs can be seen as a triangulated two-dimensional surface. Just from the combinatorial structure of the interactions of these matrices. So you're basically summing over these triangulated two-dimensional surfaces, and then you can show that the weight that appears here can be associated with some discrete GR action in 2 dimensions. Okay, and there's a continuum limit that you take, there's this double scaling limit, and I don't want to go into this, but this is basically just an example where this kind of idea that you start from something that is completely abstract and combinatorial and that has something to do with geometry. Okay? So this is well known. This has been studied since, well, the 80s at least, and people have always thought about generalizations of this. So can we do this in higher dimensions? There are tensor models that people look at where you don't have a matrix but you have something with more indices. These have attracted a lot of interest recently, also in string theory. And so this is the kind of line of thinking that I want to follow. I don't really want to propose anything that can be a full sort of quantum gravity in 4 dimensions, but I just want to write down something that is basically a matrix model that can do 4-dimensional cosmology in the sense that I described, so just homogeneous isotropic geometries that in some sense emerge from this.
So what is the advantage of this representation, and why should I be using matrices? What does it buy me?
Well, this is a way of defining 2-dimensional quantum gravity.
Okay.
So, you know, I mean,
is the main benefit that you can actually define the path integral, that you have a well defined?
I would say that, yeah.
Okay.
Yeah. I mean, these are, if you want, a very convenient technical tool that allow you a study of what is eventually a continuum theory, but in terms of these discrete structures.
How do I choose the action?
Right, so you basically choose it so that it gives you the right sort of geometric action in the end. So here basically all you need is basically, so a simple action is typically of the type where you just have a quadratic term here, and then you have some kind of interaction. So here you really want, okay, I guess you just want, let's just keep this real. You can just do it just for simplicity. So you want basically a trace of m squared, and then you have some interaction term, trace of m cubed. And so this is basically your propagator, and this is your interaction. And basically this interaction gives you these triangulations at the end of the day, if that makes sense, because the Feynman graphs will be composed of these things, so that's how you generate surfaces. So the interactions are basically designed by the combinatorics of what you want to appear in these graphs, if that makes sense. Okay, so that's one way of motivating this whole thing. More concretely, perhaps, in the application to cosmology. So if you're thinking about well, applications of quantum gravity theories to homogeneous and isotropic cosmology, the most famous example is loop quantum cosmology. So coming from loop quantum gravity, basically some of the techniques of loop quantum gravity have been applied to this very symmetric sector of GR, and you find something very interesting where you can resolve the singularity and there's a kind of bounds, and people are always very excited about these things. But these are of course very simplistic models that in some sense don't really have a clear relation to the full theory. So they have been derived in some heuristic way, but there's not a clear relation to the full theory of loop quantum gravity. So I would argue that it's necessary to somehow justify loop quantum cosmology models by deriving them from more systematically from some kind of theory, at least, that is under control. Some of you may know a bit about loop quantum cosmology, but I just want to summarize briefly. So there's been a lot of debate, and there are a bit different models, and there are ambiguities in how you define these models. But basically the model that has emerged as the favorite in some sense is, so this is Ashtika and collaborators, is basically a model where you can give a modified Friedmann equation that has a very simple form, right? So this would be your standard Friedmann equation that you know from cosmology, and now you have this correction term here where this is multiplied by some function here, right? So rho is the energy density of the matter, right? And rho c is some critical energy density, and you can see very simply that if rho reaches rho critical, then you have 0 on the right hand side, and that's where you have the bounds. So you can derive these kind of effective Friedmann equations, and these are supposed to capture some underlying physics of quantum gravity, but in order to derive these equations, you basically have to make assumptions about what is the realization of a homogeneous and isotropic universe.
Does this equation make sense as a classical equation when rho is equal to rho critical?
What do you mean by it makes sense?
I mean, is it still valid when rho goes close to rho critical, the way it is derived?
Supposedly, yes. So this is, of course, one of the very contentious points. That
so
somehow
there's no term neglected, which are like powers of rho over rho critical.
Well, I mean, you have higher order corrections in general, which are state dependent. So that's the thing. You have higher h-bar corrections because this is, of course, a classical equation. You would expect higher order contributions, but these depend on the state. So the statement is that you can choose certain appropriately designed semi-classical states such that these equations, or this equation, captures the correct physics even at the bounds. But this is a statement that comes with a lot of assumptions.
Just that's the standard loop quantum cosmology with mini superspace. Isn't that Martin Boschewald?
Right. So Martin Boschewald started with loop quantum cosmology in around 2000. He had a different model, which is not this one.
Okay,
so that's what I meant by ambiguity and controversy and discussion. People have constructed different models that can be motivated from loop quantum gravity, which differ in the details, for example, of this effective Friedmann equation. The point is, you
motivated this right? Or is that just like
well, yeah. So yeah, again, that's part of the debate. But I mean, you're using ingredients of the loop quantum gravity construction. So the quantization in particular, right? That is different from the standard quantization that you have in normal QFD. So this is used in the way it's used in loop quantum gravity, but you have to put in extra ingredients, which are to some extent arbitrary. I'm just going to draw a picture maybe to make that clearer. So one of the main things that you have to choose here in order to get to these equations is you have to choose a state for the universe. So if the universe is homogeneous and isotropic, what does it correspond to? And the simple picture that you can have, and this is in fact what's often used in these papers, is that there's some kind of underlying graph structure, which you can think of as a lattice if you want. Right, so this is just sort of one slice of this lattice. So this is regular, right? And you have a number of nodes and a number of links. And these are the structures that, of course, you also have in general in loop quantum gravity. You have these spin networks and things like that. But this is just a simple choice of such a graph that, of course, has the symmetries that you want. And in general, you have labels on these links, right? So if you know spin networks, if you don't, you can ignore this. But what happens here is that you basically put representation labels here, right? So these are SU2 representation labels, and they contain geometric information, for example, about what is the distance or the spacing between these nodes, or in different words, a kind of volume that you would associate to one node is also given by these representation labels. And the way you choose these, that's basically the main extra input that you have to make. And so in this Ashtika model, basically what you do is you fix these representations to all be minimal. So you always choose j equals 1/2, which basically means that this lattice spacing here is just some fixed length which you put in, right? So this is just a fixed fundamental parameter which you typically associate to the Planck length. So it usually comes with some numerical coefficient, and this doesn't depend on the expansion history of the universe. So if the universe is a kind of lattice like this and it evolves in time, what does not change is this lattice spacing. So lattice spacing is always the same. So in other words, you have to keep generating more nodes, right? More degrees of freedom. And that's basically the crucial difference to these older models by Boschewald, where you basically stretch out the lattice as well. So you increase the lattice spacing with the expansion of the universe. Here you don't. And that's basically the ingredient that gives you this. Okay? So in a way, then you can say that the fundamental hypothesis, and I think this is really the main ingredient, is that somehow the total volume of the universe is given by some number n, which is just some kind of number of these nodes, times some v0, right? So this is, and only n can change, v0 is always fixed. So that's if you want the assumption, okay? So if I now want to build a model that can justify this, or perhaps sort of give an indication of how this can be derived, I'm going to stick to this assumption. I'm just going to assume at a simplistic level that space is fundamentally made of certain building blocks, and these building blocks always come with some fundamental volume that I just keep fixed, and that you can set to Planckian, or it's essentially a free parameter, but it's not going to change, right? So that's basically my fundamental assumption here. Right. So one of the points here is that you make this assumption here. You start with a kind of state, and then you get some effective mini superspace model. So from all of this, you derive some kind of equation. So some kind of h psi equals 0 kind of equation, where this is now just your standard wave function of the universe, in the sense that it basically depends, for example. So this is again just simplified, but it just depends on the global degree of freedom, which is a scale factor, and say the matter field that you have, which is always this massless scalar, and that's just your standard mini superspace type model. The only difference is that this h now gets corrections, right? So this h is somehow different from what you would normally have in GR. But at this level, you don't see this discrete structure anymore. That's basically the point I'm trying to make. You only have this one wave function, which basically is just governing this global mode. And it doesn't really see this discreteness anymore. So that's what I would like to change in this model here. Okay, so in terms of the cosmological model, so I'm just going to study exactly the cosmological model that also has been used in all of these constructions, which in some sense is very nice from the perspective of quantum cosmology and has been studied by many people over the decades. So I'm just going to assume a flat FLRW universe with a massless scalar. So just a free massless scalar field. So that's the only matter degree of freedom, nothing else. And the reason, so this is not a particularly realistic model for the universe, but it's nice from the perspective of discussing the dynamics in cosmological terms. And the reason is that this scalar basically serves as a clock variable, right? Because there's no potential for the scalar, so the scalar just evolves monotonically, right? So it will always increase or it will always decrease with the evolution of the universe. So I can use it as a clock, right? It's a matter clock, if you want. Rather than using a coordinate, you actually have a physical degree of freedom here, which you can use as a clock, right? So what this means is that you can basically write the evolution of the universe in terms of, for example, the scale factor as a function of phi, or if you want to go back to this volume variable, volume as a function of phi. This is of course just a cubed. Yes?
I don't quite understand what you mean with what you mean with the scalar field is always growing. What does that exactly mean?
Right. So I mean, in the action, so the action doesn't depend explicitly on phi. It just depends on phi dot in the cosmological context, right? So phi dot is can't change sign. The momentum conjugate to phi is always conserved. It's just like a free particle. It will never turn around, right? It will always keep going in one direction. It can never turn around because there's no potential. So the scalar just keeps going. It either disappears to positive infinity or to negative infinity. Or there's of course a degenerate case where the momentum is exactly zero and you just stay at one point. So this is a case you have to exclude. But if your initial conditions have a non-zero phi derivative, you will just keep going forever. There's no potential. There's no way of turning around. So if you want to use a matter degree of freedom as a clock, of course that's something you want, right? Because if the matter degree of freedom can turn around and go back, then it's no longer a good clock because you have two instants of time which would have the same value of phi. So that would screw up the property of this being a good clock. So at turning points this breaks down, so you don't want to have a turning point. Does that make sense? Okay. Good. So yeah. So I want to think of this in kind of Hamiltonian terms, again in the context of these cosmological models and the type of Wheeler-DeWitt equation and so on. So I'm going to replace these derivatives, time derivatives, by the conjugate momenta. So this is just my notation for the canonically conjugate momenta. And then you rewrite the Friedmann equation in terms of these momenta. Right? So the degrees of freedom that I have are just now A, right? A can be a function of phi. So A and phi are the variables. And then I have these canonical momenta. So the Friedmann equation, I'm just going to show it to you. So I'm just putting basically the terms that would normally be on two sides of the Friedmann equation all on one side so that I get a constraint. Right? So this, I'm just calling this whole thing C. So C is a constraint. So it's some combination of these dynamical variables which has to be 0. Right? So this is, again, it's just putting everything on one side of the Friedmann equation. That's why there's a minus sign in front. Right? So pi phi is now this momentum of the scalar. Right? This is the energy density, goes like 1/8⁶. And this is your standard sort of left-hand side, just rewritten in terms of the canonical momenta. Okay? And that's basically all that you have. So this is your constraint. If you solve the constraint, you have physical initial data, and then this constraint also generates your time evolution. Okay? What I want to do now is just to rewrite this in a way that makes this role of phi as a clock more explicit. So this is called deparameterization. So this is a very technical word for just saying that I basically go from a formalism in which A and phi both depend on some coordinate time t to something where I basically just use phi as the clock and I eliminate phi as an independent degree of freedom. Yeah.
Has there been a lapse risk in that way of writing the constraint?
No, that's just the constraint. So the Hamiltonian is n times this. Right? So the constraint is just what it is. It doesn't involve the lapse. It just involves the dynamical variables, the phase-space variables. And the Hamiltonian would be n times this. And n is your arbitrary lapse. Can be 1 or can be some other function. Okay, so what I'm doing here is just, I'm just solving this equation in some sense for pi phi. So I'm just rewriting this in terms of pi phi. And I mean, this is very elementary, of course, and I get something like this. So I have to choose a square root here, right? So I'm taking the square root of this equation, I'm solving it for pi phi, and this basically now is an equation that you can use to define this as your, so this is, if you want, your Hamiltonian, which generates evolution with respect to this phi variable, right? So if phi is time, then the conjugate momentum is energy, right? So here I'm just solving for the energy, and I'm calling this the Hamiltonian, right? This is like you could take a square root of your usual relativistic energy momentum relation and just define that to be your Hamiltonian. Would be the same thing. So here I'm just doing it in this cosmological model. Okay. So the point is now, if you stare at this Hamiltonian, so this combination here, A, PA, or in general XP, is a generator of dilatations, right? So this Hamiltonian generates dilatations, and so I can immediately write down the classical solutions, which are just exponentials in phi, right? So, for example, A of phi is A0 exponential of, so I have to choose a sign here, and the sign choice is basically just saying whether the universe expands in positive phi direction or a negative phi direction. And that's, if you want, is conventional, because, well, it's your choice of error of time with respect to phi, right? It's just the universe played forwards or backwards. Obviously, everything is time symmetric. But the point is just that the classical solutions are exponentials, and I just have this very simple Hamiltonian here. Okay? Right. So what I want to do now is I want to have a quantum theory for this kind of cosmological model, as I said, which looks a bit like this. So I want to have a theory in which there is some kind of Fock space, if you want, some kind of quantum field theory where the fundamental quanta come with this minimal volume that I have assumed, and there's some kind of dynamics for the evolution of these quanta that has at least a chance of corresponding to this cosmological classical model in some limit, which means at late times, at low energies, and so on and so forth. So basically what I want to do is, so first of all I want to introduce some kind of QFD for these quanta of geometry that come with this minimal volume V0. So I want to have things like creation and annihilation operators for these things, some kind of Fock space. And I want to take over this assumption here that basically the volume of the universe is proportional to this minimal volume, which basically just follows from this. And I want to then define some kind of dynamics, as I said, that corresponds to this cosmological model, so it has something to do with dilatations. Right? So normally, if this was a mini superspace model, if you wanted to do something like this, you could quantize this system, and you would write down again some wave function of the universe, and it would be with respect to this kind of phi time, right? And so this would be given by, well, it would be something like A d by dA, probably a symmetric combination with some factors and so on and so forth. But now in this model, I want to really use a fundamental discreteness in the sense that the total volume should always be given by the particle number, right? So basically what I want to do is I want to go from A d by dA to N d by dN, right? And I'm putting this in quotation marks because, of course, n is discrete, right? Is a number of quanta, so there cannot be a derivative. But in some continuum limit, that should be what I have. So what you're looking for, so basically what you're looking for is some kind of Hamiltonian in this kind of, second quantization picture here that basically does this. Right, that corresponds to this kind of dilatation in the number of quanta. Okay, and basically what we realized after thinking about this for a little bit is that there is a very simple candidate for this. So if you think about quantum optics, there's a very standard process known as squeezing, right, by which you generate squeeze states from, for example, a vacuum. So this is something you do in quantum optics. These states have nice coherence properties. And if you think about it for a little bit, and I'm going to show you in detail how this works, that's probably the main technical point of the talk. You look at this, you realize that this is exactly what squeezing does if you look at the particle number. So I'm just going to explain to you what squeezing is. So imagine you have just one harmonic oscillator. So this can be like a mode of your electromagnetic field, for example, right? So these would just be operators associated to the creation and annihilation of photons in your mode. And then you can define something that is called a squeeze state, which is parameterized by some number here. That's called psi. And the way you do it is basically like this, right? So you act with this operator here, which is basically has two creation and two annihilation operators. Psi is this parameter, and this gives you what's called a squeeze state. So this, as I said, has nice kind of coherence properties, sort of saturates uncertainty relations in many cases and things like that.
Sorry,
yeah.
Are there two distinct A's, or is it the same A?
Here, no. This is A dagger. A dagger, this is AA.
So only one A.
Yeah. This is just for a single mode. So you can generalize this construction to two modes, for example. You can have these two mode squeeze states. Here, this is just the simplest possible case. You just have one mode. Okay. So if you now compute the particle number in this state, right, this is just your number operator as A dagger A, you can derive this expression here. It's just given by sinh squared of psi. And so when psi is very large, positive or negative, this goes like an exponential of psi. Right? That's just an elementary calculation. So this is exactly what we're looking for, of course, because we're looking for something that kind of has an exponentially growing volume or particle number. Here, given with respect to this parameter psi, of course, which doesn't have an interpretation as time, but of course then it's very easy to replace psi by something that's time dependent. So that, if you want, was the main insight here. I mean, you can show this more explicitly. So you can call this squeezing operator e to the minus I psi little s, and then you can show that if little s acts on some eigenstate, so this is now an eigenstate with the particle number n, this in a continuum limit again is basically exactly what I wanted to have before, which is this kind of symmetric combination of this dilatation operator. So this is a continuum limit. So that's just another way of showing the same thing, right? Either I'm just looking at the explicit solutions and see what they do, or I can just look at the action of this operator and I see that it really generates dilatations in the way I was proposing. Okay, so what you see is that this is kind of a very natural candidate for the Hamiltonian of this very simple kind of toy model where I just have these chunks of geometry and I want the volume of the universe to follow basically the classical Friedmann equation, at least at late times. So that's what we did basically. Maybe to make this a bit more interesting, just another little motivation here for how this can be put into a bigger context. So the theory I normally like to work on for this kind of quantum geometry is called group field theory. And this is something I've also discussed here a few times, I think. And there you have a similar picture in some sense. So you also have field operators, you have creation and annihilation operators, and you have fundamental quanta of geometry. However, in the general case, these come with additional structure. So I'm just going to give you a little sketch of that, how that works. And I'm not going to discuss this in any detail because I don't have time. But so what you have in group field theory is you also have creation and annihilation operators that can be derived from actual field operators. So these are field operators. This is a complex scalar field if you want. And the arguments of this field, so these are elements of some Lie group, for example SU2. This would again be your matter degree of freedom. And what these things do is they can create quanta of space that basically look like this, just with more structure. So if this guy acts on the vacuum, so again you have a Fock space, you have some vacuum. The vacuum corresponds to absolutely nothing, so no geometry at all. And if you act on the vacuum, you basically get your elementary building block, which you can picture as a tetrahedron. And these G's are basically group elements associated to the links, right? You have 4 links that go through the 4 faces. The tetrahedron has 4 faces. And this phi is just a label you put on the middle. What this means is sort of an elementary discrete chunk of geometry where these G's are basically parallel transports, right? So they give me some kind of discrete connection data where I can parallel transport along these links. And if I do that, I have to use these group elements. And the phi is just the value of that the scalar takes, if this is my matter degree of freedom. And so these are the variables of, if you want, the lattice gauge theory, and they're also the fundamental variables of loop quantum gravity, right? Of the loop quantum gravity is formulated in terms of these holonomies of SU2. So this is kind of, if you want the connection, this is a more general picture in which you have these additional local degrees of freedom that you somehow associate with a discrete connection, and ultimately with gravity, right, with gravitational degrees of freedom. Here I'm just truncating all of these degrees of freedom because I just want this regular homogeneous isotropic universe, so I'm not interested in local excitations of gravity. So I'm basically considering, if you want, a truncation where I'm just ignoring these group degrees of freedom, and I basically end up with some kind of creation and annihilation operators. So these can in general come with some discrete indices. So this is just A1 to A4 and B1 to B4. These indices are again just combinatorial. They're just discrete indices that you can use to glue these things together. Again, like in the context of the matrix model earlier, but they don't come with these additional group variables. If you want this to be more rigorous, you can basically expand these functions on the group in representations, and again, you can just fix all the representations to be j equals 1/2. But that's, again, it's just a technical comment for how you do this truncation if you want to do it. Right, so in general, these are, if you want, there are degrees of freedom here that in general can allow you to change the shape of these chunks, right? They can come with different sizes, with different angles, and so on. And I'm just ignoring all of these degrees of freedom. I'm just assuming that all of these are just of a fixed type. That's just the same. Okay. So I probably don't have a lot of time left, but I've kind of given you most of the main points. So what we did in the project now was just to combine all these insights basically together and cook up a model which basically uses a squeezing operator as the Hamiltonian. So that's kind of the obvious thing to do after what I've told you. So you can, for example, take these creation and annihilation operators. So these are a bit more complicated now than just a single one because they have these extra combinatorial indices. But that's basically just a difference in counting, right? There's just a number of these oscillators now. That's finite. So I'm not going to bother you with the details, but the point is that the Hamiltonian is now essentially just what I had before. So I now have these internal indices here, and I'm just going to I'm just going to write them as one index here because the details are not too important. And I'm contracting these indices with some kind of invariant tensor here. And so this is just the most straightforward generalization of what I had before, right? Which is this the squeezing operator. And so you can, just by construction, you can immediately solve this model, right? You can write down the general solution of your Schrödinger equation, which again is just given by some kind of squeezing of your initial state. Now you have phi as well, right? Because phi is your time variable. So this is just, I'm just taking e to the iht, right? Essentially. So this is just writing out the same thing as before, acting on some arbitrary initial state, right? So this is just a general solution of the Schrödinger equation, just by construction. I just take e to the iht acting on some initial state. So this is slightly more general than what I had here. I mean, there are more oscillator modes now, and I don't necessarily start with a vacuum, but I start with some generic initial state. But other than that, it's very similar. So I'm just, in this model, I'm just generating a squeeze state out of some initial state by acting with this Hamiltonian. And that's basically going to correspond to an asymptotically very large universe by the same argument as here, because the number of quanta just grows exponentially with respect to phi. Right? So now once you have this exact solution, you can just look at what it does, right? So you define some operator here which corresponds to the volume. So this is again just what I had before. So this is some number times the number operator, right? And so you can look at the evolution, for example, of this expectation value. So that's the most elementary thing you would calculate. And if you do this for this state, you just find that it basically does what it should do. So as phi is large, positive or negative, you have this V0 here. Then there are some numbers here. These just depend on psi 0. But they're just fixed, right? They just depend on the initial state. And then you have this exponential growth. And note that this grows exponentially both as you go to positive infinity and as you go to negative infinity. So what it does, if you want a sketch here, is it basically interpolates between the classical contracting solution and the classical expanding solution of your classical Friedmann equations. And in between there's some kind of quantum regime, if you want, where you deviate from the classical dynamics. And you can show that in general there's some non-zero lower bound here, so you actually never reach 0. And this is, here you would have the sinh squared, which would essentially be the same thing, only that it goes through 0. And that's just because I started with the Fock vacuum, right? The Fock vacuum, of course, has 0 particles when I start. So that's the only point at which I actually hit 0. If I start with anything else, I start with a state of 1 particle, for example. I'm shifting this, and I actually never go through 0. So the point, I should probably close, but the point of this model now is that if you just look at what it actually does, and you study these explicit solutions here, so what do you find? So you find, essentially the point is that you find almost all of the features of these LQC models. So you find, so of course lambda here is a free parameter, right? So you have to set lambda to square root of 3 pi g, and then you actually have the correct classical limit. So what you have the classical Friedmann dynamics at large volume, right? So when the universe is much larger than Planck scale, you just satisfy what you have in classical cosmology. So this is just n much larger than 1. It actually happens quite quickly as you follow the dynamics. You have a bounce in the sense that you never go through 0 volume, right? Which is of LQC type. So it's actually very similar to what you see in this effective models, to the point that you can actually write down an effective Friedmann equation and basically has this form. So that's how you characterize this kind of bounce. And moreover, you have a very semi-classical state at large, well, at very early or very late times, just because of the properties of this squeezing operator. Which is, of course, in general, is a very important question if you have these quantum cosmology models, right? Why would you ever have a semi-classical state? Usually you have to kind of put something in there. Here it's somehow more natural because the dynamics sort of at least preserves these semi-classical properties. The point here is, of course, that, I mean, this is just a toy model, and it's, of course, been cooked up to do what it's supposed to do. But, of course, this has initially nothing to do with the Einstein equations, or even with GR, or anything we know about classical gravity. It's an abstract model that has these kind of fundamental combinatorial degrees of freedom, and has a dynamics that you've borrowed from quantum optics. And what you find is that this model basically reproduces exactly the kind of cosmology that you would like to have. Mm-hmm.
So, I mean, if you have any scalar field and you have any FRW space-time geometry, that will lead to the squeezing of this mode, where you get 2 mode squeeze states. So what I'm saying is, okay, of course, if I look at my field and I see what the geometry is doing to it is squeezing it. Mm-hmm. If you then say, can I express that directly through the squeezing operator? Mm-hmm. I would say, yeah, naturally.
Okay. I mean, here there's of course no space-time to start with. There's no geometry to start with, right?
The effect of the space-time geometry onto those modes is that you squeeze.
Yeah, that's certainly true.
I'm a bit puzzled a little bit about some of the things, but yeah, I mean, what that expanding universe is doing to these modes, it creates 2 mode squeeze states. Mm-hmm.
So you're basically saying one can reverse this argument and say that squeezing would also be responsible for the expansion in some sense.
It is a way of creating two-mode squeeze state, and you can rewrite that in one-mode squeezing if you want as well, if you have closed boundaries. So yes, in fact, in analog gravity, that's a way of generating this kind of squeeze state.
I mean, yeah, as I said, the formalism is of course very different here because there's no space-time to start with. So there's no space-time in which these fields live. They're just purely abstract structures. But there may be, there may be a general argument of this type why these things have to be related. So that's a very good point.
So maybe one thing which is indeed interesting, if you just have a squeezing operation, in some sense, what's the difference, right? What's the difference with exactly mimicking inflation, for example, with analogs, or just have a quantum mechanical system where you have squeezing operators?
So you're saying it can be made more abstract from that point of view, or more general?
It's more abstract.
Yeah.
And can you produce the so you say I have a field, and I do either I have an effective space-time geometry, or I have some squeezing operators. Can that be completely identical at the end when I get?
Right. That would be the question. Yeah. Yeah. That's very interesting. Okay. So yeah, scientifically, this was basically what I wanted to say. So that's just the model that we cooked up. What can we learn from this? I think I would say it's one step towards making this kind of relation a bit more rigorous, because you have a dynamical system in which you can generate these quanta, right? There's really, the number of these quanta can change dynamically. There is a quantum field theory underlying it. I don't have to assume a fixed state here and let it there for all times, but I kind of see how these things emerge dynamically, sort of just from solving the Schrödinger equation. I mean, you may postulate that there is some kind of symmetry-reduced sector of loop quantum gravity or group field theory that would have to look like this squeezing in some limit or in some regime. That's something I can't really argue for in more detail, except that here there really was some kind of truncation of this full theory setting. So if you could do this also at the level of dynamics, maybe you could relate this to a proposal for the full theory dynamics, which would of course be what we would ultimately like to do. Yeah, I think that's basically it. Yeah, thank you.
Anybody has any further questions for Steffen?
I have a question which you kind of answered already in the last comments. The question was, what are you planning to do with all this? What are the future plans?
Right. Yeah, I think, well, ultimately you would like to use these insights as some kind of recipe for restricting the type of dynamics also for more complicated models that have additional degrees of freedom. Because in some sense I would like to see this as at least, what I said, as a kind of reduced sector of a more full theory dynamics. Of course, they are usually, I mean, we have studied these kind of more general condensate states also in group field theory, but there you have to do very drastic approximations and truncations, which are not really fundamentally justified. And so perhaps there is a way of generalizing these models to have something in between, right, in which you add more degrees of freedom without having to go to the full theory. So that's really the hope I would have.
Any other question? So if your scalar field had interactions and it wouldn't increase or decrease monotonically, right? Wouldn't that be a problem in going to the step where you just de-parameterize?
Yeah, absolutely. In general, yes.
So how would you deal with that? I mean, in the real universe, things do have interactions.
So this is, of course, a very general question about how you describe evolution in relational terms, right? I mean, fundamentally, coordinates don't mean anything. You should always identify matter degrees of freedom, and you should always identify clocks somewhere in the matter. So this is a general question that many people have been talking about and writing about. You could try to do things perturbatively in a certain regime, of course, where interactions are maybe not dominant enough, but these will always break down at the turning point. So whenever you have a turning point, this kind of construction will no longer be viable.
I mean, the classical level coordinates in this respect are just a useful way to impose your causality restrictions, right? I mean, and if you don't have the interactions and you can deparameterize this way, you know, you have a trivial relation between time and one of your fields, so things become easy.
Right. I mean, in a way, in all of these models, if you want, this is a price to pay for background independence, right? I mean, you have a theory which only uses gauge invariant quantities in some sense, and doesn't have coordinates at the fundamental level. So anything that is supposed to serve the role of a coordinate has to be reconstructed in some sense from the variables that you have, which are typically the matter degrees of freedom.
What you really need to introduce somehow is the causal structure. So have you thought at all about how this will affect your construction?
I mean, of course, yeah, in general, as you say, you can have a valid causal structure and still have matter degrees of freedom that no longer serve as clocks in some regime. These things are not necessarily in any one-to-one relation, of course. Yeah, in general, what you would like to do, at least, is to add perturbations to this, right? To even study the propagation of small excitations on these things and then see if there is a useful notion of causality. So that would be the thing to do. But you would have to do it in these background independent terms.
Okay, so let's thank Steffen again.